Hello, everyone, and welcome to The Vertical Space, a podcast at the intersection of technology and flight. We are your hosts, Jim Barry, Peter Shannon, and Luka Tomjanovic, and here we look at the most important forces shaping the market of advanced air mobility with a particular focus on why and how they matter to those building a business in this very exciting and growing industry.
I think there's a real opportunity to have a very high specific power, low specific energy cell, and very high specific energy, low specific power for range, right? So you use one kind of battery for cruise and another kind of battery that can take care of the landing and the takeoff mission. And if we can pull this off, that's going to fundamentally break this AND trade-off. There's a lot of pieces that's needed for this around DC to DC converters and other pieces at the system level, which is slowly falling in place. So I think soon we'll start to see some of these hybrid battery packs, not hybrid in the sense of what we usually think of hybrid, but now two different cells as the hybridization.
Welcome back to The Vertical Space. Today, we revisit the topic of batteries with Venkat Viswanathan, Associate Professor of Mechanical Engineering at Carnegie Mellon University. As someone who relatively recently started his journey in electric aviation, Venkat is massively inspired by the challenge and opportunity of electrifying aviation. We sat down to discuss why he is so optimistic about 1,000 watt-hour per kilogram energy density at the battery pack level becoming commercially available in the next 10 to 15 years, a goal that many of his fellow battery experts find tough to believe. However, this is not a, quote, boring lesson in battery chemistry. We talked about what it takes to commercialize new battery chemistries and who will carry the burden of funding new R&D to improve battery energy and power densities now that there is no incentive to pursue such efforts by the automotive industry. Listen also how Venkat describes the AND problem, which stands for the challenge for batteries to achieve both high energy density and also high power density, and how hybrid batteries with different chemistries might help solve this challenge. We also talked about the differences between batteries for VTOL versus CTOL aircraft, about the different and sometimes conflicting requirements for different types of aircraft and missions, about innovation in non-destructive diagnostics to figure out power and energy remaining, and also about how generative AI can accelerate the development of new battery chemistries. As mentioned, Venkat is an associate professor of mechanical engineering at Carnegie Mellon University, but he's moving to the University of Michigan Aerospace Engineering in the fall of 2023. He's a recipient of numerous awards, including Alfred P. Sloan Research Fellowship for Fundamental Research and MIT Technology Review Innovators Under 35 for Translational Research. He's the co-founder of Aonics, a company commercializing machine learning-guided battery materials discovery and optimization for electric vehicles, aircraft, and space. And he's also a co-founder of And Battery Aero, a company commercializing battery systems for electric aviation. Enjoy the conversation with Venkat after a brief sponsor message. This episode of the Vertical Space podcast is brought to you by Avionics. Avionics is the leader in low size, weight, and power certified avionics for manned, unmanned, and advanced air mobility aircraft. Let Avionics help you achieve your goals, whether that be type certification, airspace access, or beyond visual line of sight operations. Avionics has certified and certifiable communications, navigation, and surveillance avionics for your aircraft. So head over to uavionics.com or Google it to see how you can start flying safer and move your platform forward into shared airspace.
Venkat, welcome to the Vertical Space. Great to have you with us.
Thanks, Jim, and Luka, great to be here.
This is a real honor to have you on, Venkat. A lot to talk about. So our first question, is there anything that very few in the industry agree with you on?
Yeah, so one thing that I think most people disagree with me on is the trajectory of what is going to be possible with battery-powered aircraft, especially in the advanced air mobility. I've stuck out on a limb and said that we would have battery cells and then associated packs that would have energy density of approaching 1,000 watt-hours per kilogram at the pack level. And what this would enable is long-range eVTOLs, in the range of 300 to 500 nautical miles. And so I think this is the arc of what I think will happen in the battery technology. Even my battery experts disagree with me on this, but we'll see how the next decade shapes up.
What is the timeline for this assumption?
It's a 10 to 15 year timeline for this assumption.
What would that imply in terms of an annual growth in specific energy density between now and then? And what has been historical growth? And what are some of the main assumptions that you're basing this viewpoint on?
Yeah, this is a fantastic question. So if you look at the macro perspective, right, over about 150 years from 1850 to about the 2000s, we doubled the energy density from sort of the lead acid to where lithium ion was. But if you look at where lithium ion batteries, so that started about 1991, and you look at how that has progressed over the last 30 years, it has progressed at the rate of about 2 to 3% per year. If you zoom in over the last decade, it's progressing around 4 to 5% per year. That doubling may not sound a lot, but if you double the rate of improvement, that compounds pretty quickly. But if you actually zoom in even more and zoom in and look at what has been possible over the last 5 years, 2017, the best cells that you could get were about 250 watt hours per kilogram. So that's energy that is packed per weight of the cell. So you weigh the cell and you look at the energy that the cell can deliver. Now, if you look at what is possible today, there's numerous announcements and credible scaling of technology, both with batteries that are based on silicon and lithium metal that are about approaching 500 watt hours per kilogram. So that's almost a doubling in the last 5 to 6 years or so. And so the assumption is that we have an incredible rate of improvement, and I think we're going to get into that in more detail. But the assumption is that the fact that we have incredible innovation related to machine learning and all kinds of new characterization tools that will allow us to innovate much faster. And over the next decade, we should expect another doubling.
So just doing some quick math, is that assuming a roughly 10% annual growth rate for the next 10, 15 years to reach that 1K watt hours per kilogram at a pack level?
Yeah, at a pack level, yeah, about 10% per year is what we're hoping can be done.
Which is double of what we have observed in the recent past.
Right, exactly. So there's been sort of one doubling from the early 2000s to the 2010s to 2020, and we hope that there'll be another doubling in this next decade.
And staying with the question, why do people disagree with you?
Yeah, I think it's
what would most very competent people, Venkat, say is the more likely path?
Yeah, so I think most people would think that the likely path is incremental improvement of lithium-ion batteries. That means that we have a very stable technology stack with the use of graphite as the anode and the use of various kinds of oxides, nickel, manganese, cobalt, iron phosphate. So these all go by various acronyms, NMC, LFP, NCA, and that we are not going to move away from this material stack. And I think if you look at the options available, there's lots of technological options that are going to break the limit of what is possible with graphite and any of these oxide cathodes. And I think most people think that it's very difficult for any of these other technologies to scale. And they're very pessimistic about the timeline of how long it'll take to resolve the remaining scientific challenges. And maybe I'll tell you one anecdote that I think is very instructive. In 2019, if you'd asked people that worked on one particular kind of battery technology associated with lithium metal, you would have gotten a 90-10 answer that 90% of them would say that this would never be solved, and 10% would say that this would be solved very quickly. Fast forward 2023, right? I think now it is sort of ubiquitously agreed that the whole sort of lithium metal problem is solved, and now the main thing is to scale the technology. And so I think this is sort of the challenge where most people are very pessimistic about how quickly they can solve scientific challenges. Batteries are hard, and I think we're going to dive deep into that. But I think that's why they tend to disagree.
And Venkat, I wanted to get into this a little bit later, but you've given a good introduction. We're going to ask you to tell us about batteries, their origins, and the like. But I'm sure a lot of listeners want to know, given the claims that have been made by a lot of the eVTOL companies, let's say, electric aviation is being manifested in many different ways. But a lot of the organizations that potentially are pushing the capabilities of electric and batteries, some have said are the eVTOL companies. Do you generally believe, from the ones that you've read about, especially those that are public, that battery technology is going to be allow them to be able to accomplish their missions and their promises over the next 5 to 7 years?
Yeah, so we wrote this paper in 2021, late 2021, in the Proceedings of the National Academy of Sciences. And the intent of that paper was to analyze the energy efficiency of urban aircraft. So that paper had two figures. First figure was comparing the energy efficiency of eVTOL aircraft compared to internal combustion engine vehicles and electric vehicles. And the second figure was the technology readiness level of eVTOL aircraft for the stated range and missions, and whether battery cell technology was available for that. What ended up happening is we thought the first figure would be the most important point of the paper. It ends up being that the second figure, which is now widely used, this is sort of called the AND chart now, where it plots the specific power and the specific energy. And we work with a number of eVTOL companies there to assess their claim and work with them to sort of figure out what their range payload plans are, and then assess that. And the short version is that I'm very optimistic that most of them have cell technology that would allow them to be near term ready for commercialization, except for maybe one or two where their power requirements are very high because of a certain architecture that they chose with their small ducted fans. Most other designs have a good combination of the kind of power they need for takeoff and especially landing, and then the kind of specific energy they need to achieve the hundreds of miles of range that their stated mission is.
All right, so I would love to get into more detail just on that chart, because that's on page 2 of the paper, for, as you said, the PNAS paper. And I have seen it in so many places, and I've known you or known of you for a year and a half. I never even realized it was yours. It's been quoted in so many different places, Venkat. So we'll talk about that hopefully later. So please tell us about batteries, origin, and their application to aviation. And please talk a little bit about, the start of aviation and how fast things progressed with fuel, and how you see the same occurring with batteries as well.
So actually, when we wrote this paper in Nature, we actually started with an anecdote from 1884 about the La France airship, which was actually powered by a 435 kilogram zinc chlorine battery. It was a 17 watt hour per kilogram battery, so much less energy dense than even lead acid battery. It was the first controlled flight, and its inventor Charles Reynard, proclaimed that electric aviation powered by batteries was just around the corner. About 35 years have passed in the intervening period, and we're still waiting. And so if you look at the arc of batteries for aviation, one of the critical metrics is specific energy. And very quickly you can convince yourself that battery powered electric aviation is very difficult, because even the best batteries that we have today have specific energies in the range of about 250 to 300 watt hours per kilogram. And then when you put that together into a pack, then you have about 200 watt hours per kilogram. These are based on lithium ion cells, the same kind of cells that are used in automotive and portable electronics. The gap between that and jet fuel power, the usable energy density possible with jet fuel, right? You have a factor of somewhere between 15 to 20, right? So it's in the range of about 4,000 to 6,000 watt hours per kilogram usable specific energy. So the arc of batteries for electric aviation in the recent past has largely, as a result, been limited to aircrafts that can do very short range, and of course, some options involving hybrid, where they try to shave the peak power out. And so as batteries improve, I think the emissions and the capabilities will increase. But at present, right, we're very limited in terms of the kinds of use cases that batteries see in electric aviation.
How much has the penetration of electric ground vehicles, cars, influenced innovation with electric aviation, do you think?
Yeah, no, this is a fantastic question because this is actually one of the premise for a workshop that NASA and DOE put together first in 2017 and then again in 2019, and then one that happened actually just a week and a half ago. And the question that they asked was, would aviation batteries be significantly different, or can they just piggyback off automotive batteries? And so, for the most part, especially urban air mobility, all of the eVTOL companies today are leveraging batteries that have largely been produced for automotive. And that's great. And I think that's been really amazing for getting the volumes, getting the pricing down, and getting performance that they could have otherwise not been able to fund themselves in terms of, what's the R&D needed for a cell company to produce that technology. But now I think there's a deviation. Automotive requirements today are largely driven by cost. And you can see that there's actually a trend backwards where they're switching from higher energy density NMC or NCA, nickel cobalt, nickel manganese cobalt, or nickel cobalt aluminum based batteries, which are much higher energy density, to kind of battery, which is with lithium iron phosphate, which is much lower energy density, almost in the range of about 150 compared to sort of 250 for these NMC and NCA batteries, largely driven by cost, because automotive has gotten to a performance level where cost is the primary axis that they care about. Range and other factors are largely solved for them. And so the future arc of aviation batteries is significantly different than automotive batteries. And you're seeing that now, where it was the consensus at this NASA DOE workshop that aviation batteries will require their own development, will require their own innovation stack, very different from automotive. And the divergence is here, and the divergence is today. And so it's critical for aviation battery companies to sort of emerge as on their own and look for delivering aviation specific performance.
So, who do you think will carry the burden of further development in batteries to meet the next level of requirements for aviation? Is the demand that's out there in the market perceived as significant enough to attract capital for companies that are observing what's happening in aviation outside of the industry?
Yeah, fantastic question. Because to first order, to commercialize a new battery cell chemistry is about $1 billion. That's the capital required to wrap up the R&D and then get a line that would produce off order a gigawatt hour or so. And so that's significant capital that needs to be invested to be able to get a technology there. Fortunately, I think there's a few key things that are emerging, and actually the timing of this podcast could not be better because we're at a historic moment where later this week, ARPA-E is organizing a workshop to put together a program. Dr. Hala Cheeseman is leading an effort to try and produce battery cell solutions that would enable the so-called BAT1K, the 1,000 watt hour per kilogram battery. And so what you need early on is someone that can provide some patient capital that can allow you to test and tinker before you scale. And I think with batteries, there are many, many ways to fail, right? And very few ways to succeed, because the size of bad options far, far larger than the size of good options in terms of getting to the answer. So I think this is going to be a really tricky combination. I think cell companies have to emerge here. And I think it's going to be probably new players. It's not likely that the traditional automotive cell suppliers are the ones that are going to corner this market.
Venkat, you've mentioned, and I think it was in Nature, I'm not sure which article it was, you mentioned the difference between the use of the batteries for the car versus the use of the batteries for aviation. And you mentioned the first thing you have to solve for aviation, and you have to keep in mind, is safety. Just talk a little bit about that. I know our audience generally knows this, but it really makes a whole new set of challenges, doesn't it?
Yeah, absolutely. So safety is a really critical aspect, of course, in automotive as well, but even more so in aviation. So obviously, battery fires associated with lithium-ion batteries many of us have read about them. And this largely comes from the fact that there are two possible ways. One is defective manufacturing. So basically, for no reason at all, one in, some ratio, right? Billion, 100 million, a cell will go into what's called thermal runaway, otherwise known as fire. And this happens because the batteries inside short for some reason. And that means that there's basically an electrical connection between the anode and the cathode. And then there's a surge in current. And the fire stems largely from the fact that there is a liquid inside, there's a liquid electrolyte that, largely is like gasoline. It's an organic compound, flammable. And so that produces very large amount of energy, which then it gets released as heat and causes fire. And so there's a lot of interest in trying to figure out options that would be safe for aviation. So there's a lot of innovation on trying to identify ways in which you stop after a cell goes into thermal runaway to stop it at the pack level, right? That is, one cell goes into thermal runaway, but then that doesn't propagate to the adjacent cell. And so that fails safely, right? So there's a number of efforts that are aviation specific, where thermal runaway propagation, the kinds of thermal management solutions that are being looked at for aviation, quite different from the simple passive or liquid cooled solutions that are there for automotive. In addition, people are looking at ensuring that they could have better options for safety by more advanced battery management system. So this is the computer that sort of controls the batteries and how much power they deliver, how quickly they charge, and so on. And so this is going to be, of course, an evolving discussion, but I think there's going to be really critical, because safety is going to be of paramount interest if batteries have to get into the air.
Give a little bit of a discussion on electrification of batteries with aviation overall, where we are today, and then also what's driving the need. I mean, at the end of the day, people have said there's an awful lot of organizations that are saying we want electrification in batteries, but the best way to start with the most dramatic effect is fixed wing using runways, not VTOL. And then what's driving the need for VTOL, and what's the power difference between a fixed wing using a runway and a VTOL? And then give a perspective on sustainability. Sorry, long question. On sustainability, it's the bigger aircraft that are really going to make a difference with sustainability. But, we've talked a little bit about this in the past, but give a perspective to our audience, size it up. Because at the end of the day, some may say, why do we even need it for aviation today? What's really driving it? And isn't it the big aircraft that really have to be solved for?
Yeah, this is a great question and a lot to unpack there. So let's do the first part, which is the power requirements for conventional takeoff, CTOL, versus vertical takeoff, VTOLs. So the major difference is that once you have a runway, then because of the fact that you have runway, the power needs to take off and climb, and then, of course, descend and land, are much lighter on the battery per cell than vertical takeoff and landing. And so to give some numbers there, I'll just define one unit that I think is very important in the battery industry that hopefully your listeners can grasp, which is called C rate. The idea of C rate is if you discharge all of the energy that's contained inside the battery in 1 hour, that's 1 C. If you discharge it in 30 minutes, that's 2 C. If you discharge it in 2 hours, that's C by 2 or 0.5 C. So higher the C rate, the harder it is for batteries to deliver that kind of power. So today's batteries can relatively easily do maybe 1 to 2 C. Higher than that, it starts to struggle and it gets exponentially difficult. So to get to something like 6 C or 8 C is very, very difficult. So most conventional takeoff missions are at 1 C or below, right? So which means that it's very comfortable for the battery, right? It's very easy for the battery to do. VTOLs, on the other hand, because of the vertical takeoff and landing, require, depending on the aircraft design, right, anywhere between 4 to 10 C, sometimes even more than 10 C. And so the batteries inside, and I describe this as basically being on ludicrous mode, right? Except that, ludicrous mode lasts for 3 seconds. Here, it may last for, up to a minute or two. And so that's the kind of strain we put on the battery on every mission. And so this is sort of a really monumental challenge where VTOL cells are going to be very, very different than CTOL cells. And so now switching gears to the second question that you asked, and this is one I think, I think about a lot, right? So most of my research group, right, is the students that join my group are extremely passionate about sustainability. So sustainability is what drives them to join my group and then work on these, extremely hard problems. Now, you're absolutely right that as we see it today, electric propulsion, that is battery powered electric propulsion, is likely to maybe address the regional aircraft market and then maybe get to narrow body by late 2030s, early 2040s. And the wide body long haul aircraft are unlikely with the arc of where we are today in terms of even the kind of cells and packs that we're talking about. And so wide body would need even higher than the kinds of numbers that we're talking about here, which are already extremely aggressive. But I think it's, the reason it's very important to work on these technologies, especially electric propulsion, right, is it's hard to imagine where you would get to a decade or 2 decades from now. If you looked at in 2003, if you looked at where we were with the Tesla Roadster, right? It was 110,000 plus car. Batteries were costing, over $1,000 per kilowatt hour, and it could produce only a 200-mile range. And if you asked even the best expert at that point where electric cars would go and whether it was feasible in a 15-year time frame to have a close to mass market electric car that would be, in the $30,000 to $40,000 price range while still delivering, 250 to 300 miles, it would be, most would say that it's impossible, right? So, we try the impossible so that, even if we get to something in between, I think it'll unlock various other markets. Most importantly, I think the pursuit of a very high specific energy battery cell chemistry will have many, many downstream consequences in sustainability. And so I think as it stands today, right, sustainable aviation fuels may represent sort of one of the leading options for decarbonizing long-haul aircraft. But I think it's very difficult to, as the saying goes, right, future is extremely difficult to predict, right? The only future you can predict is the one you invent.
It's worth highlighting this because there are a couple of well-discussed facts when it comes to the emissions that are being generated by aviation. One of them was even quoted by your paper in Nature that says more than 95% of aviation emissions come from aircraft with more than 100 seats. There's another sort of data point that we've heard from the FAA that says the flights over 1,000 nautical miles represent 20% of operations, but 65% of total fuel burn. So if somebody is really into solving emissions issue for aviation, batteries arguably are not the place that they would go to. However, I think the primary argument, at least personally, in my opinion, for electrifying aviation, even the small end of aviation, is in safety and in cost, on operational savings, in maintenance. And that really enables, in the short term, perhaps a renaissance in general aviation more than helping decarbonize aviation. And certainly it is an investment in the future arc that you highlight.
Yep, completely agree. One thing that is instructive is we wrote this very interesting paper on electric semi-trucks. And there's a similar question around operational efficiency that is really important there, right? When you're carrying goods, right, the value proposition is the cost, the dollar per mile. So what we found there was, in most scenarios, within a couple of years, an electric semi-truck is much cheaper to operate because of the operational efficiency. So the energy efficiency associated with the fact that you now use less energy, less electrical energy compared to chemical energy, as well as less maintenance, right? And so I've personally seen this, right? I've owned a Tesla Model S for 8.5 years. I've had almost, other than sort of normal maintenance, I've had no issues over this period. So I think all these, operational benefits, operational efficiency gains are going to be super critical.
So can you talk a little bit about the complexities of bringing an electric aircraft to market, right? Given that we have batteries that can support, at least some use cases in things like training, yet it's been 3 years, almost 3 years, since certification of Pipistrel Velis, which was the first one that was certified with an electric propulsion system, albeit in the light sports aircraft category, but still. Would you have expected more certifications by now?
Yes and no. I think obviously, as your audience very well knows, right, the cost to get any new aircraft certified is very, very difficult. And so I think there's only a few companies today with sort of the capital war chest to be able to get that through certification. And obviously, the Pipistrel team is incredible for what they have pulled off, right? So kudos to Tina and his team for whatever they've accomplished. And obviously, I think they're truly pioneers in terms of the kinds of risks that they took. Right, I saw a presentation in 2019, and the kinds of things they tried. Certainly, are extremely ambitious in terms of how they put battery packs together and just flew. Right, so it's very much in the Wright brothers style in terms of risk taking. I think now it's more clear, given how much we understand how to build an electrified powertrain, how to build in safe electric propulsion systems. I think, now it's looking more likely, given that there are several companies with the kind of capital needed to be able to certify their aircraft. So Joby and Archer have submitted their airworthiness certificate criteria, in sort of November and December of 2022. And I think it's going to be interesting what happens in the next few years in terms of how that evolves. But I think it's always the devil's in the details, and there's a lot of details to be worked out, especially around safe electrified propulsion systems. And we don't have perfectly safe electrified propulsion systems even for ground vehicles. So I think certainly I'm not surprised that things have taken longer to get things to certification.
Both examples are eVTOLs that you mentioned, but what about conventional aircraft that are being electrified? What's the state of certification with that use case, with that category aircraft?
I think there's a number of efforts. I think here many of the hybrid electric cases are probably much further ahead than the all electric cases, because the all electric cases inevitably, for their business cases to make sense, likely require some improvements in specific energy of batteries. So they're all waiting their time to ride the few percent per year improvements so that they can get cells and packs that are much more energy efficient. Ampere has made some great progress in terms of actual miles and flying with their hybrid electric aircraft. So I think we'll see in that regime hybrid electric as sort of the first use case, and then we'll see more all electric cases getting certified.
Do you know what are some of the specific remaining biggest hurdles that the regulators want to see from the industry before awarding type certificates for electric aircraft? What are you hearing from the regulatory circles about the biggest fears and milestones?
Yeah, so I'll focus my discussion here around the battery side. So the canonical document, the DO311A, is sort of the main standards document that one uses to assess battery packs. And of course, that was written in the context of the Dreamliner fires, right? So they were not imagined to be propulsion battery packs, right? They were imagined to be battery packs for auxiliary power. So if you look at the standards document, right, the highest energy category that they go to is a few watt hour, right? And of course, any of these aircrafts would have kilowatt hours, maybe even megawatt hour of capacity. So I think there's a lot of discussion both at the FAA and EASA around how to modify that and how to get that to the level where the remaining hurdles of ensuring thermal runway safety and so on, because the safety burden imposed by the original DO311A is extremely stringent to be able to demonstrate that the battery pack is safe. And so there are sort of various ways in which companies are going about demonstrating that their battery packs are safe from thermal runway. And this is, I think, one of the key factors that is holding things up in terms of being able to demonstrate that if one cell goes into thermal runaway, or a few cells in a string goes into thermal runaway, that you can safely avoid the whole pack failing, and can then lead to safe operation towards landing or emergency landing. I think this remains one of the critical hurdles on the certification piece for the battery packs.
So it sounds like there's two sort of parallel discussions here when it comes to guesstimating timelines for adoption of electrification in aviation. One is on the development of the battery chemistry and battery cells and packs. And then another one is how that trajectory crosses with the regulatory safety-centric approach and making sure that all the possible contingencies and edge cases are predictable and well understood and can be managed. And so the latter certainly will add additional cost to ultimately, energy density at the pack level. So when you combine those two paths, what is a realistic and reasonable timeline for, number one, development of battery cell technology, but also number two, getting the regulators comfortable?
Yeah, this is a great question, right? So it adds cost and also weight. And I think the second hurts, of course, the ability to close the aircraft design, right? So I think here's where it's extremely important that companies that are trying to commercialize new cell technology work very closely with aircraft makers, so that they can understand the complexities and challenges early on, and figure out issues that they may run into later on. And that's, I think, going to be really critical, as especially companies that are trying to specifically address this market. This is going to be a critical piece here. And I think as companies try to set themselves up in terms of how to be successful, I think a multi-stakeholder approach where you're actively getting feedback both on the regulatory side as well as on ensuring sufficient safety, redundancy, etc. I think this is going to be a critical piece for companies in this space to succeed.
Which eVTOL companies today are pushing the bounds of batteries more than others, where you're really impressed with what they're doing, but they may be leaning in a bit more than you would think they would need to, given the vehicle they have? And which ones are using existing battery technology today? And although they're not pushing the bounds and they're not perhaps as innovative on the battery side, they're more likely to be successful because they're using today's technology.
Yeah, this is a great question. I think in our paper, we highlighted a couple of aircraft that can very easily and comfortably do their mission today's cell technology, right? So Archer, for example, and you've had Jeff Power as a guest on your podcast, talk through their approach of being conservative and sort of leveraging this piece of being able to make the mission work today with today's cell technology, and not waiting for breakthroughs in the future. Now, Joby, on the other hand, for example, is using conventional or near state of the art cell technology, but then combining it with their pack innovation. John Wagner and his team are doing exceptional work on packing efficiency and being able to get a very high energy efficiency pack, right? So well over 200 watt hours per kilogram at the pack level. So they are certainly working hard on that. Lilium, for example, has a partnership with Zen Labs, which is now called Ion Blocks, to try and bring a new cell chemistry with silicon, which has much higher specific energy, but also simultaneously having to deliver very high specific power. So Ion Blocks there. So this is has been a great example of the kind of co-innovation that we've been talking about that's required. Ion Blocks has shown data that shows very promising performance for being able to deliver high specific power with their silicon anodes while still having battery cells that are in the 300 watt hours per kilogram. Now, of course, devil is in the details. The question is whether this can be scaled up and commercialized in the time frame that's needed, and how will that play into certification and regulation, as we talked about. I think that's sort of the state of play today of batteries in the eVTOL space.
Venkat, what's the and problem and how do we solve that?
Yeah, so the and problem for aviation batteries, especially in the eVTOL space, right, is twofold. One is you need very high specific energy, that is energy per weight of the battery pack to get long range. And you also need very high specific power, that is very high power per weight of the battery pack, for safely landing or doing an aborted landing mission. The main challenge is batteries are closed systems. That means that batteries don't change weight as you fly, as you discharge and charge. The same reason why they're amazing also causes a fundamental trade-off. This trade-off is called the Ragone trade-off. Actually, David Ragone was at Carnegie Mellon when he wrote this seminal report showing this trade-off that batteries can either give you very high power or give you very high energy, but not both at the same time. And so the problem is that eVTOL, especially urban air mobility aircraft, need both high specific energy to get long range missions, as well as high specific power to be able to deliver the power needed for safely landing. And so this has been one of the critical challenges for cell technology that they can use, because this is not something that you can just pick up readily off the shelf from an automotive cell, because the automotive cells are not designed for this. The automotive cells don't need to deliver such high specific power, especially at low state of charge, because nobody asks for, oh, can I do 0 to 60 when I have 20% range in my battery? But no, I want to do the 0 to 60 over and over for 30 times, right? So that's sort of the mission of an eVTOL battery. And so this is sort of the problem of eVTOL batteries.
What technology or insight exists today that Ragone didn't have at the time when he was making this seminal paper that makes it possible to break this paradigm?
Yeah, so I think what you can do is the trade-off is fundamental, but where the trade-off occurs can be pushed. That is, at what point of the specific energy, specific power combination does this trade-off become knee dropping, right? That is, it just catastrophically fails. And so the way in which you do that is you bring down all the resistances inside the cell. So you bring down the resistances associated with how fast the ions can move inside the electrolyte. So there's been a lot of electrolyte innovation that has enabled fast discharge and fast charge, because the electrolytes conduct the lithium ions much faster and much better. So this has been through additives engineering by putting custom things in the electrolyte that enables fast discharge and fast charge. There's been other innovations in terms of the electrode thickness. So how thick you make the electrode, so you make it moderately thick, not too thick, so that you can still get very high specific power. So there's a number of these innovations. And then fundamentally, the last one is some chemistries are inherently capable of higher specific power. And this has to do with the fact that the reactions that happen at that interface have a much higher intrinsic rate. And so the place at which this AND problem manifests itself is much later. And so that allows you to simultaneously deliver very high specific power at 4 to 8C while still being able to have very high specific energy.
If you're saying that we fundamentally will not solve the AND problem, are we just saying that we will use systems engineering to go around some of these trade-offs?
Yeah, I think that's a great perspective. I think we will certainly move the frontier of where the AND boundary is, right, in terms of how much energy and power that it can deliver, but simultaneously, integrating that with, taking a systems engineering approach with the aircraft design and how you design in redundancy with, how you split the power from the battery pack to the electric drivetrain. I think these factors are going to be critical in making sure that we don't push the operational requirement of the battery packs beyond the sort of AND boundary that's set by Ragone.
How realistic is it to assume multiple different chemistries within battery packs on an aircraft?
Yeah, no, this is one that comes up many times as we discuss even battery packs for electric vehicles. So for example, the electric vehicle use case also has a very similar challenge where most of the time you take short trips and then occasionally you take a long trip, right? So what you can do is you could have a battery that has very low specific energy that you use all the time, but has a very high cycle life so that you can use it every day. And then you have a very high specific energy battery pack that only kicks in when you need to go the long distance, right? And so for a long time, hybrid battery packs have been discussed, but not seen traction. We're starting to see that in electric vehicles, where our Next Energy is a company that is trying to commercialize a system that has low specific energy, high cycle life, high specific energy, low cycle life battery pack. Similarly, I think there's a real opportunity to have a very high specific power, low specific energy cell, and very high specific energy, low specific power for range, right? So you use one kind of battery for cruise and another kind of battery that can take care of the landing and the takeoff mission. And if we can pull this off, that's going to fundamentally break this AND trade-off. And I think there's a lot of pieces that's needed for this around DC to DC converters and other pieces at the system level, which is slowly falling in place. So I think soon we'll start to see some of these hybrid battery packs, not hybrid in the sense of what we usually think of hybrid, but now two different cells as the hybridization.
Is anyone trying to commercialize this, to your knowledge?
I don't know. I don't think so. Maybe that it's a great startup idea for someone that's out there trying to do something in the space.
How much of the AND problem and what element of it has to be solved for a single aisle aircraft to, I think you've said it's going to take 20 to 30 years to electrify with batteries the single aisle aircraft. What part of the AND problem is going to have to be solved for that to be accomplished?
Yeah, so there the main thing is being able to deliver very high specific energy, while at the same time being able to deliver high cycle life for operational cost. So if you imagine, these single aisle aircraft, fly several times a day, probably will recharge at least a few times a day, right? Even if you had 1,000 cycle battery or 2,000 cycle battery, right? A few times charging a day, right? So you're replacing these battery packs every 6 months or so, and of course that adds enormously to the cost per mile flown. And so there, being able to get very high specific energy, very high cycle life is the AND problem. And if you look at any high specific energy battery today, they're all very low cycle life, right? So for example, lithium air batteries is a technology that I've worked on during my graduate studies at Stanford, and those only could cycle for tens of cycles, right? But they were capable of, well over 500, closer to 1,000 watt hours per kilogram, but, very low cycle life, right? So if you look at many other options, so lithium CFX is another option where, this is actually a battery that's used today in aerospace in the black box. These cells can deliver over 800 watt hours per kilogram today, but they can only be used once. So the main challenge for enabling single aisle, the BAT1K challenge, as I like to call it, is to be able to get that specific energy while also delivering extremely high cycle life. So somewhere between well over 2,000, approaching 5,000 cycles.
Listen, one of the reasons we're talking is you made a big announcement saying you're moving to the University of Michigan. So tell us about the 4 transformative events that led you to Michigan.
Yeah, no, this is one that a lot of my friends have asked. So I think you're on top of your game. Electric vehicles are the most are seeing amazing traction. Why are you moving to University of Michigan's aerospace department? I think it's very important to.
But Venkat, I think you're part of the mechanical engineering department today, right?
Yes.
And you're moving to the aeronautical engineering department at Michigan.
Yes.
That's a big deal.
It's a big change. And so I think there are 2 parts to that answer, right? So one is the department change is, why is that important, right? The departments in a university are a symbol of the kind of students that you attract, right? So if you're in a mechanical engineering department, you have people that have a passion for cars, of course, other things, but one sort of canonical way to think about it is, they love, things that move on ground. Now, in an aerospace program, people are united by their passion for flying objects. And so one of the challenges that, I've been facing is, increasingly the future of my research program has been going towards aviation. And so being part of an aerospace department, I thought was the right path forward. And so University of Michigan has one of the oldest aerospace departments. So I think it's fitting to go and try to take the oldest aerospace department for the second century of aeronautics and aviation. How do we get here, right? And it's an interesting journey. So I've had an electric vehicle for many years. In 2017, I did this road trip from Pittsburgh to Palo Alto. I was going to spend that summer working at a battery startup called QuantumScape. And so my wife joined on that trip begrudgingly. We drove, instead of, I guess the other route would have been flying. And it was interesting to realize that even at that time in 2017, the trip was relatively easy to do. I mean, range anxiety was there, right? We did land, we did get to superchargers at, a few miles of range left. But to a first approximation, I thought that all of these battery innovations that I'm working on, right, these next generation battery innovations, are they really going to see the inside of a car, right? Is that the right place for them to go? And so, that was sort of an existential angst that I had. And then when I got back, one of my colleagues, Yetming Chang, introduced me to Alan Epstein, who at that time was at Pratt & Whitney. And, for a year, I reported to him, and, he taught me all about aviation. I taught him all about batteries, and, I became incredibly fascinated by this topic. Then the second, transformative event happened. Jeff Bauer, who you, of course, we talked about earlier, he was then at Airbus Vahana, and, we got introduced from a mutual friend, and he came and asked, well, can you help us, understand batteries for eVTOLs? And it was a fascinating opportunity. And so he funded my first electric aviation project when we knew nothing on that topic, right? And so, thanks to Jeff for taking that big bet on us. He taught us a lot. And by the end of that project, we knew an enormous amount.
This is when he was at Airbus?
Yeah, he was at Airbus.
So what did you learn during that period?
Yeah, so we actually, I think the first version of this and question we wrote actually in that first paper that we co-wrote with him, where we realized that the kind of batteries needed for eVTOL have this additional specific power requirement. That's something that, most people in automotive don't even test for, right? So if you took a cell maker and asked them, what's the highest specific power you can deliver at 30%, they probably didn't even test it, right? It's not one of the requirements that you test for in automotive batteries. So that was one of the eye-opening things that I learned. And the second thing we learned there was in that journey, we realized how difficult it is to forecast the ability of the battery to deliver that power, that 30-40% state of charge. It's very easy when you have a battery to estimate how much energy, or at least relatively easy to estimate how much energy is left in the battery pack, right? That's what you get in an EV, right? It tells you how much range you're capable of, right? But for an eVTOL, what you need to do is to be able to forecast whether your battery pack is capable of delivering that landing power, right? And not just when it is fresh, but when it is aged, and you don't know how badly it's changed while it has aged. And so this is a very challenging requirement for eVTOLs. And I think this is actually one of the main scientific hurdles that eVTOL makers are facing, right, in terms of being able to forecast whether you can get that specific power for the landing.
Is this an opportunity for entrepreneurs to innovate in? Is this a science problem, or is this a product and engineering problem?
I think it's a combination. I think it's a combination of science and product engineering. I think clever ways of doing diagnostics on the cell non-destructively, right? I think adding more sensor suite on the battery cell and pack would be great. I think figuring out other ways in which optimally aligning the mission and the battery configuration, I think, is another system level opportunity for startups to think about.
So this is not a mere issue of collecting voltage or some really basic metrics from the battery.
Yeah. So basically, to first approximation, right, if you just had voltage, current, and temperature, which is the three typical things that are collected at the cell level, at the cell and the module level, that's not sufficiently granular enough to be able to forecast how much power is left in an extremely reliable way. So there's, I think, real opportunity for additional information that I think would be extremely useful, especially in the eVTOL context.
Venkat, what about drones and commercial drones? How will the development in batteries impact that segment of aviation, of advanced air mobility? And how are the requirements for those different from the requirements that we've been talking about for eVTOLs and eCTOLs?
Yeah, I think the drone requirement is actually quite aligned with the requirements from a cell level from the eVTOL requirements that we talked about. So I think the arc of improvements that we're going to talk about, that we talked about in terms of what can increase operational range and, of course, being able to forecast specific power and things like that better, I think that's going to have trickle effects on drones, where drones are now going to be able to have much higher operational range and time, which I think is going to be a significant boost to that industry. And I think, the opportunities there, the fact that, you don't have to carry passengers allows you to push the frontier even more. And so I think there's going to be, a lot of exciting innovation in that space. The challenge always is volume, right? So, you have to probably have 1,000 drones that would sort of make up one eVTOL, right, in terms of volume of batteries, right? So I think drone specific innovation might be, a little further out. So I think pigging on eVTOL cells for drones is going to be a very attractive opportunity.
We read and hear a lot about large language models like GPT in the news lately. How does GPT change the picture in battery chemistry designs? How can people leverage it to accelerate the timelines?
Yeah, no, this is a fantastic question, and one that a different part of my group really focuses on how to use the innovations in machine learning in scientific materials and discovery and innovation. So the interesting thing about battery materials is that when you have to design a new battery component, say an anode or a cathode, right? That's the two electrodes, or an electrolyte. The chemical space is very large. So, for example, if you wanted to change the electrolyte, right, you have over 6 billion molecules that is synthetically accessible very easily that you have to choose from. Or if you want to change the electrode, right, you have over 10,000 known lithium containing compounds, even for a lithium ion battery, right? So what that means is that the space of options is very, very large. And so large generative models are going to be extremely helpful in helping design next generation battery materials. The key is, just like what we are seeing, right? The core enabling piece for large language models is to be able to tie in with other APIs, right? So, the utility of when, you connect a large language model, to your, travel app or other things, right, to do tasks in the same way. The key will be to be able to pair these with systems that can do things in the real world, right? So that can test. And so here, I'm extremely excited by the possibility of combining generative models, like ChatGPT and others, with autonomous testing systems. So we built actually two such systems called Auto and Clio. Clio is a robotic electrolyte test stand that basically you can control completely, right, via an API call, right? So this is a robotic test setup that is housed, at Carnegie Mellon, and you can programmatically, request this experiment to be done or that experiment to be done. So what that allows you to do, right, is in a sense, right, when ChatGPT has a connection to the internet, right, it's much more useful. In the same way, if these large language models are then allowed to get feedback, right, real hardware feedback, that will allow them to innovate much faster, right? Today, we use a software called Dragonfly, which was developed at Carnegie Mellon, which is a sort of a Bayesian optimizer to sort of decide what to do next. But imagine what we could do if we could navigate chemical space so much better than the sort of these small models that are sort of narrowly searching over the chemical space. So I'm extraordinarily excited by the possibility that is enabled by this. And so one of the reasons, right, this is one of the reasons why I've been closely involved and co-founded this company called Aonics, which is at the frontier of this, where they're using large language models and other machine learning models to discover new battery materials and then be able to test them and then scale them and then deploy them in various electric mobility applications.
Venkat, first of all, I asked Jeff Bauer a very similar question to this. What is a guy like you who does what you do during the day? What do you do for fun?
Yeah, this is a great question. I think some of the fun things are I like tennis a lot. I think sports is a great way to to decompress, and it allows you to relax. Some of my best thoughts I've had are while playing tennis or playing badminton, and so sports allows me to decompress a lot. I think that would be my main
That's great.
outside activity.
One of the hurdles for electric aviation, eVTOLs and like are batteries. And you've given us a really good background on, where do you see those that are perhaps lower risk and some are higher risk? What do you think is the biggest misconception of investors when it comes to electric aviation and eVTOLs?
Yeah. So I think one of the main challenges, right, is that most investors overestimate what is possible in the short term, right, and underestimate what's possible in the long term. And I think with battery innovation, things just take time. But slow and steady progress, allows you to do things, over a few month period, you might think that the progress is, not too great, but over a few year time horizon, right, the progress can be, quite astronomical. And I think this is the sort of challenge in, many of the deep tech companies and deep tech technologies, is that time is not something that you can just solve or shrink by just putting more capital. And so I think this is one of the things that I think is very challenging when you try to innovate in the space, is because you need to have time on your side. You need to retire the science risk and the technology risk in a way where you can do that before you take, investor capital. And so this is also another piece of advice for entrepreneurs. Look for avenues where you can get that patient capital and also external validation, right? And here I'd like to acknowledge what ARPA-E has done for me in my own career, right? So ARPA-E, was an agency that was created around 2009 and has, I think, fundamentally transformed how innovative companies are created and are supported through the arc of the full innovation cycle, right? And so one journey that we had was in this lithium metal cell technology that we developed, right? The first funded project was in 2016, right? And from there we de-risked some pieces in the first 3 years. Then we had another extension for another year and a half. Then we're now in the scale up phase, right? So it would have been over 10 years where we have been patiently supported, and of course, critically assessed over this entire period, ensuring that the milestones are still aggressive, right? But aggressive in a way that are technologically sound and valid, so that you can actually achieve them. And so I think this is one of the things where pairing investor capital with the right kind of non-dilutive sources is, I think, going to be a critical piece for entrepreneurs as they think about innovation in this space.
And so 5 or 10 years from now, what do you see the industry looking like? And I have to ask you, you've talked a lot about helicopters. Not a big helicopter fan, you are. So as you look out 5, 10 years, what do you see as the future of batteries with electric aviation? And if you don't mind, give your perspective on what may occur with the helicopter industry, given the advances you see happening in batteries and electric aviation.
Yeah, so one of our favorite places to visit is New York, and if you're by the Hudson Yards, right, the one thing you realize is how annoying helicopters are, right? So they land and loud. I think if batteries are just able to solve the helicopter problem and displace every helicopter in the world, I think that would be success. And I think it's not far off where battery powered eVTOLs are likely to have range and mission capability that could displace a majority of the helicopters. I'm going to offend all my helicopter colleagues at Michigan with this, but I hope that happens.
As you were making your decision to go to Michigan, you took a long time to make that decision. So why was that, and why is it relevant to our listeners?
The decision is, of course, it's a big one, and these decisions are a one-way street, right? So you want to be very thoughtful about the decision. One of the things that I was wondering whether this is the problem that I am going to spend majority of my time solving over the next decade or so, that is enabling battery innovations for aviation. And so one thing that happened late last summer that fundamentally transformed my thinking here was that with my former student Shashank Shripad, we spun out a company called An Battery Aero from our RPE program to commercialize battery systems for electric aviation. And through that journey, when we, obviously the and is now a wordplay on the and problem that we have talked about in great detail here. And in that journey, right, we talked to a lot of aviation companies. And what we realized was that, finally, when they talked to us, right, they instantly got it, right? Here was a group of people that really cared about aviation and understood batteries at the same time, right? That sort of knowledge of both spaces positioned us in an incredible way. And now we've added Thilo Brahn, who was one of the early members of Lilium. And so we have an incredible team that I think is going to make a fundamentally transformative impact in battery-enabled electric aviation. That journey over the last 3 to 6 months really pushed me over the hill. Right? It is clear that batteries and battery innovation, people that are working on material innovation, they are going to have a ball with the aviation market, because whatever innovation you come up with, whatever specific energy target you hit, there's a new market that you can unlock. And there's endless possibility. And the last thought I want to leave your listeners with is, with batteries, we are far, right, very far from the limit of what's possible with batteries, right? So we're about a factor of 10, maybe even more, from what is the theoretical limit of known battery chemistries, right? This is just known from what we can achieve today, right? And so we're very, very far from what's possible, right? So I think just like semiconductors had 4 decades of Moore's law, right? I expect that we would have at least another 2 or 3 decades of improvements at several percent per year into the next sort of 20 to 25 years. And so there's a lot of very exciting things that lie ahead, and hopefully many of those innovations will take to the skies.
Thanks, Venkat. This was fantastic. Really enjoyed it. Thanks for your time.
Thanks a lot.
All right, that's a wrap for today. Thank you for listening to the Vertical Space Podcast. Reach out if there are topics that you would like us to discuss, and goodbye until the next episode. Unless mentioned, this podcast is in no way endorsing or promoting any person and or company mentioned, and all opinions within the podcast are solely that of the presenters. The Vertical Space makes no guarantees, warranty, or representation of any information given in this podcast. Any information given is for informational purposes and should be used at your own risk. This podcast is for general, educational, and entertainment purposes only.